Okay, so our first topic, the next one in line, is the implicit differentiation. So we've only worked with explicit equations. Those are ones when the variable on one side is, so y equals, and there is an explicit formula for it. Implicit would be things like this example here, where there's two variables in the equation. It's not quite connected. Now, it's not such a bad thing to deal with the implicit differentiation. I'll show you some situations where it's actually a lot nicer. But we want to work with the Leibniz notation for this, which was these little dy by dx's. So just remember that this is the derivative of y with respect to x. Okay? So when we differentiate with respect to x, like you've been doing so far, life is not so bad. It's not so complicated. Just we could apply our rules to it. But if we're differentiating with respect to x and the variables don't agree, okay, how would you differentiate y when you want to do this with respect to x? Well, what you have to think about, sort of what's happening behind the scenes, is the only way that this makes sense is if there's some relationship between x and y. So for example, I don't know what this relationship is, but maybe they're saying y equals, I don't know, sine x plus x squared, or some connection back to x. Okay? So that way, if I'm doing it in terms of y, this is like a chain rule question. There's no x's in my derivative here, but there's a relationship. So the derivative for the outside piece would be 3y squared, and then I have to differentiate it however that connects to x. So if you then told me how y is related to x, then I could fill in the rest of this derivative. Okay? So when we work with two variables, it's important that you keep track of who you're differentiating for. So for example, in the next one, it's a pretty simple derivative. It's going to be 1, because I'm differentiating with respect to x, plus 3 times dy by dx. That's the derivative of the outside function, which is 3, and the derivative of y, dy dx. Okay, so try the next one. See if you can figure out implicitly what would the derivative of xy squared look like. Okay, so for this one, you could still apply the rules that you know, but you just have to be careful about keeping track of whose derivative you're taking. So this one's going to be a power rule question, and it's going to be the derivative of x times y squared plus x times the derivative of y squared with respect to x. So that means it'll be 2y times dy by dx. Okay? So far that's the only real new part of this, is that you can't forget the extra piece here. When you're differentiating with respect to x and the variables don't match, you have to keep track of those missing derivatives. So now I'm going to show you how this actually works out and why it's to our advantage to know this. There's a couple of techniques we're going to learn. So here's the way I usually do these. Oops, hang on a second. So just to give you some guidelines here, the three things that I usually do is first I differentiate everybody with respect to x. So differentiate all pieces with respect to x. Okay? That's what we just practiced. We just practiced differentiating with respect to x. And the next thing that we're going to do is we're going to move all the pieces that have a dy dx to one side of the equation and factor them. So this step may sound strange, but when you see us actually do it, it'll make more sense. So move all dy dx pieces to one side and factor so that we can solve for dy by dx. Okay, so here's a curve that I've given you, and it's defined implicitly. I don't know that there's any easy way to figure out an explicit formula, There would be an easy one, obviously, in terms of x, because it would be easy to solve this equation for x. But that would also involve some square roots, which is going to bring in a chain rule. There's going to be lots of extra calculus to do. So I'm going to show you how this works if I do it implicitly. Okay, so the first thing that I mentioned was we want to differentiate everybody with respect to x. So that'll be 3y squared dy dx plus 2y dy dx minus 5 dy dx. And that's just regular derivative for x squared, so I know it's minus 2x. And the derivative of negative 4 is 0. Okay. So here are the pieces that I was talking about that have a dy by dx. So what I want to do is move them to one side, which conveniently they already are, and factor them out. So here's what I would make this look like in the second step. Factor them out will be dy by dx, and the pieces are 3y squared plus 2y minus 5 equals 2x. So they were moved to one side, so they'd be all by themselves, and I can factor it. The reason I did that is now it's very easy to solve for dy by dx, which is the derivative of y with respect to x. This is now a formula that I can use in a calculator. Which would be 2x over 3y squared plus 2y minus 5. So let me make some sense of what we just did for you, okay? I'm going to show you some pictures of what we just did and how this group of equations, we wouldn't be able to do this without... Here, I'll move that in case you're still copying. Yeah. Oops. Well, I know, I'll move this down. Okay. So the equation was y cubed minus y squared minus 5y, and then sorry, there's a plus there, and minus x squared equals negative 4. I think, let me just double check and see if that was right. Y cubed plus y squared. Yeah, okay, so that looks right. So let's actually take a look at this curve. So that's what the curve looks like. It's there. Can you see tangent lines fitting anywhere on this curve? Or is it doesn't work because it's in, the graph's not explicit. Can you put a tangent line on there?
Yeah.
Visually, can you see tangent lines on this thing? Right, so we should still be able to find derivatives. Okay, so let's find one now and actually make sense of what we did with that derivative. Here's an easy point right where these crosshairs are. That would be the point 5 for x, 3 for y. Okay, so where that crosshairs is here, let's find the tangent. Okay, so maybe I'll make, just to have some extra space. So let's find the derivative. So before, when we had a derivative, we only worked with x. Our formulas only had an x in it. And whenever I asked you for the derivative, you only needed to use the x coordinate. Well, now, there's x's and y's in this derivative. So that means there's going to be, both coordinates are going to be needed to calculate it. So to do this, it's 2x. So that'll be 5 for x. And 3y squared minus, what was it, 2y? And, help me out here, minus 5?
Yeah.
Sorry, trying to just go off of memory here. Is that filled in properly? Yeah. Okay, so if I was to go and calculate this, it tells me the slope is 10 over 28. So just to show you that we haven't just done this process doesn't fail because there's two variables. Here's my slope, and here's my point. I'm going to show you the actual tangent line on this graph. Okay. So the slope was 10 over 28. Y was 3. So here's the equation for that line. So now hopefully this thing just skims the graph right on that one spot where it's supposed to be tangent to. Okay, so that line comes shooting across, and it's hard to see. Maybe I'll zoom in a bit more so you can see that it is actually a tangent line there. Let's go from 0 to 16. So there you can see it just skims right by it and keeps going off. It is the tangent line there. We can still find it even though there's two variables. Okay, so that's actually what we've been doing with this equation. Okay, so there's a typo here, so we're just going to cross this one out. But what I'd like you to do, an ellipse, that also is an oval. Same thing as an oval. I'll show you the equation, and we'll find the line as well. Find its derivative implicitly, and see if you can figure out what will the tangent line look like at the point 2, 0. Okay? So find your inverse derivative, or sorry, find your implicit derivative, and then use the point 2, 0 to figure out the derivative there. Okay, so I'll try and catch up to you here. Okay, so this should be your implicit derivative. It requires both an x and a y value. So let's substitute and see what we get. This would be -2 over 0. Okay, so come on, good calculus students. What do you think has happened here? It died. Really close.
We divided by 0 and it burst into flame.
It's a vertical line, yeah. This is the slope that's undefined. It's a vertical or an infinite slope. So like, for example, we were talking about a constant divided by 0 goes to infinity. So this is going to be a vertical line. So if we take a look at the equation for this and see if that actually makes sense. Let me clear this off. So if we go from, I don't know, let's go from -4 to 4. And the equation that we were dealing with is x squared plus 4y squared equals 4. Is that equals 4? So there's the ellipse, the oval. And does it make sense that the tangent line's undefined there? Does that make sense to you that it should be a vertical line? So there's the tangent line at x equals 2. It's a vertical line. Okay, so we are still finding these derivatives. It's just now we may have more than one variable. So here's one reason why this is a preferred approach. If you were to consider, this is the bottom half of the ellipse. If it was positive, it would be the top half. This is your alternative to find that derivative. Solve it for y and then try and work with the one derivative. That's a lot of extra work. We don't need to go that far. We can use just this implicit form and find the same information. Okay? There's no chain rule here. There's no solving for y. It's ready to go as it is. So that's one advantage to this approach.